Hi, my name's Jacob Enon, and this is my demonstration video for my A2 computing project. I've developed a system around message decryption, encryption, and digestion using Python. First, I'd like to demonstrate the various encryption functions that are available. When the program loads, it brings up a main menu where the user can pick to either encrypt, decrypt, or hash their message. So you choose the relevant algorithm, and then it will open up this window. So I'm going to select Morse, and you enter the plain text, and on pressing start it will just output the ciphertext there. Next we'll test the Venam cipher. So as before, I'll enter the plain text, and then on pressing start it will generate a random one-time pad, which is the same length as the inputted plain text, and will output the ciphertext. And as unlike the Morse, all of the following algorithms have a key, it will tell the user what the key is so that they can decrypt it later. Next, I'll test the division cipher. I'll also use this chance to demonstrate some of the advanced options available. So rather than typing out lengthy plain text, you have the option to read from a file. So when I click Browse Files, it opens up this Windows Explorer, and I can select this plain text, which I prepared at home. And then when I click Set Options, you can see that it's printed this text into the plain text box. This allows the user to ensure that they've selected the correct file, and also makes processing a lot simpler, as it doesn't have to read from the file as it processes. So when I press Start Now, it outputs the ciphertext and the randomly generated key. Finally, we'll test the Caesar cipher, and I'll also demonstrate how you can write to a file. So here I have an empty file which I'll be using later, and if I run the program again, select encrypt, and this time I'll also demonstrate the enter key. So if I choose 12, then I'll read from the same file, and I'll write to the empty file as you saw before. I set these options. This time when I press start, rather than outputting to the plain text box, it brings up this message saying that it's been stored to this file location that I chose. So if I navigate to that file, you can see that it's got the plain text that I was encrypting, the encryption, and the key that I selected of 12. I'd also like to demonstrate what happens if you try to encrypt a Venam message with a user-defined key that is shorter than the plain text you're trying to encrypt. Under the rules of Venam, the one-time pad you're using has to be at least as long as the plain text. So in this case, when my key is much shorter, when I press start, the program will pick up on this and generate its own random key for you. As you can see, it's not the key I've used, but one that is just as long as the plain text I was originally using. Having now demonstrated all of the encryption functions, I'll demonstrate everything that the decrypt function can do. So to start with, I'm going to enter this plain text back in my encryption system and encrypt via a Morse to give me a sample text to run through the decryption. So here you can see that it's outputted the same. It's printed all in lowercase because the standard Morse code doesn't differentiate between upper and lowercase, and to make programming easier, I've converted all of my inputs to lowercase. One fundamental aspect of the decrypt function that I was quite keen to include was this unknown option. So when you're decrypting, a lot of the time you're not going to know what algorithm was used. So I'll demonstrate this for now with the Morse, but when I come to do more complicated algorithms, you'll see how advanced it is at deciding which algorithm of these have been used. So, as you can see, without being passed that it was Morse I was using, it still returns the same plain text. Here I have some sample data that I've created ready to test my Venam decryption. So, if I select Venam, you'll see that it says if key is known. So if I start trying to just decrypt my ciphertext, I'll get this message come up. So if I go to the advanced options and input this key, now it outputs the same plain text there. For these next decryptions, it's more than just applying an algorithm, so I need a lengthier piece of ciphertext to perform proper frequency analysis and compare it to a dictionary which I've got in one of my resource files. So if I now run this, I'll demonstrate the Visionaire encryption. So I'll select my ciphertext and I'll write it to, say, an output file. So it takes a lot longer to run because it has to calculate the length of the key and find what each item of the key is, and the key I've used for this encryption is quite long, so the longer the key and the longer the text, the longer it's going to take. But as you can see now, my output, it's the ciphertext it was demonstrating with, the plain text, and this is the key that it managed to find. Finally, I'll test the Caesar cipher, and I'll also demonstrate some of the additional features. So here I've got another plain text. Now you'll notice this at the bottom. So I've designed this plain text, this ciphertext, sorry, to not follow the standard English frequencies. So this is designed to throw the algorithm, and so if I run it under normal conditions, under decryption, when I read from a file this ciphertext, when I try and run, you'll see that it searches for a while but doesn't actually find a solution. So this is under the normal searching. However, the program is able to write the analysis it finds to a file. So if I just create a file here, this outputs the frequencies that it managed to find, which can be useful if you're trying to do any other analysis on the file, even though you've not solved it, but I will now demonstrate how you can solve the problem. Another file that I've got here is this sample plain text. So I used an algorithm to generate this text, which is supposedly plain text that follows similar frequency patterns to the letter that I'm currently trying to decrypt. So I talked about this in my acceptable limitations and how I would get around it. So if I now run the program, you'll see as well that I'm using the unknown, and I believe it's still able to calculate what it is. So I use this ciphertext, and here I provide plaintext samples. So if I use this, what this does is before it attempts to analyze, it will read this file and create a new frequency table rather than the standard one I'm using, and it will try to decrypt using that and see if it can make any more sense out of what I've got here. So if I run this now, very quickly, it gives me, as you can see, this was a Caesar cipher which it managed to work out on its own, and I've now got my plain text. The program's not going to be able to crack every single code that you get there. So if I run this example, then with no advanced options, it will pass the code. I'll let it know that it's Visionaire. It can still sometimes have problems finding the key because under the algorithm I'm using, it can find many different potential keys, and so if a certain number of them don't work, then it can be deemed that none of them are going to work. So I'll just click no for that. But now, as you can see, I'd have the key here. So if I run the code again, and enter the known key, and set that, you can see that the program can be helped, so you can find a more efficient solution, or sometimes it won't be able to find the solution without certain options, but this is how you can use the options to get a more efficient route to the answer. Now I can move on to demonstrating the hash function. So this window comes up a little bit differently, where you have the option to pick any from a vast range of algorithms available. So this many algorithms are made available through OpenSSL, and so in my testing I used SHA-512 and MD4. So for some variety, let's use this one, and as you can see I can pass any test data and it will hash it using any of these algorithms. I wrote my hash function with a variety of different uses in mind, but one key one is password storage and password protection. So adding a salt before you hash data will add random data to the plain text and then pass that to the hashing algorithm. So that way, even if the user is able to guess the correct password, it is still useless to them, as they don't know what salt has been added, so they won't be able to get the same hash to get into the database if that's what you were to use this for. So if I set that, let's mix it up again with a different hashing algorithm. Now when I run it, this is obviously difficult to demonstrate as you can't reverse a hashed algorithm, but in my screenshots I've demonstrated with some shell outputs the hash that's being used. When hashing passwords, for example, the rule is that you can't reuse the same salt. So what I've done is I've created this function, which is a new salt per line. So when you input your passwords or whatever data it is, every time there's a line break, the program will create a new salt and add it to that line, hash that line, and then output it. So I'll also show this split output. So this is designed to be used with writing to a file. So rather than outputting what your plain text is and then your relevant, not ciphertext, your hash, it will just output the hash so that that is safe to be stored then. So if I write this now, when I start, that writes to a file. As you can see with these shell outputs, these are the salts that I've used, so as you can see they are different each time. And if I navigate to that output file, it has output these hashed passwords but has not stored anywhere the unhashed data for security purposes. Finally, I'll show you this one last advanced option, which is to set the salt length. So if I set an example of 3, obviously in real circumstances you would use a much longer salt length. Generally the standard is that your salt is the same length as the actual output of the hash, and I've used a standard, so if you don't set this option, I've used a standard of 16. So these were the salts that I was using on my last test. So if I set these options, now when I run this, I'll just set my variable salt again. When I run this, you can see that clearly the salt, while insecure, has been changed. So you could, realistically, you could change this to a longer salt if you were very tight on your security, but that's down to personal preference. Finally, I'll quickly run over this information page. So it brings up this empty text box, and these act like a tabbed text box. So here it provides some information about the system I'm using and the algorithms that are focused around encryption and decryption, and my source for all of the data I've used and everything I've learned about encryption, just down here. And if you switch to this tab, it gives you a bit of help on how to use the system and the general standards the system uses, the advanced options and everything you would need. So I've read this data from a file for memory efficiency, so it can be quickly accessed within the program. However, the user is perfectly capable of finding these files themselves. So if they wanted to read this outside of running the program. They don't need to boot the program up to view it. But that concludes everything I wanted to demonstrate in this video. Thank you for watching. As one final note, I would like to point out I'm aware that the window has jumped around the screen a bit. That's simply that Windows opens the program in a slightly different place each time, and is unavoidable, so sorry for that. But please refer to my documentation for everything else that I have referred to in this video, and for the rest of my testing and my screenshots. Thank you.